Greetings. This is Hugh factors, or well, that's short for huge factors, with another video for you, which we hope you'll enjoy. And we'll start out. This is a really amazing bit of nice math that is fun and it teaches a whole lot. So I wrote at the top here, it says primes are a very loopy journey towards infinity. Well, if you look at the prime numbers 2, 3, 5, 7, 11, 13, and so forth, you might guess that they go on forever, but in math, you have to prove it. And that's not always easy, but we can prove something about an infinity here, and that is really cool. We can really, for real, prove that the primes do go on forever. And that's actually exciting. And let's look at how that can be done. You gave us two primes here, 3 and 7. And we can multiply them together. That parenthesis means multiplication here. And a big insight is to add 1 to that. So what do we get? 3 times 7 plus 1, that's 21 plus 1, that's 22. And that is an output, I'm going to call it here, because this relates to computers and your cell phone and lots more. That's our output. And there's something to notice here. Notice I put a big concept alert. If we consider 22 and we divide it by this prime number 3, we get 7. And 7 times 3 is 21, and we get a remainder of 1. That's because of this 1 we added right here. Aha. Now if we divide 7, our other prime number, into 22, 3 times 7 is 21, and once again we get a remainder of what? 1. So for any prime number in this list right here, we only have 2 so far. When we divide it into our output, we get a remainder of 1. That's a big, important concept here. Okay, now we have to look at our output, which is 22. It might have been a prime, but for the numbers you gave, it's not. 22 can be factored into 2 times 11. You may have made factor trees before. It will be interesting to see later on that, all our green rectangles, all our money is protected by prime numbers. So these factor trees are important in real life. So 22 is 2 times 11. That gives us 2 more prime numbers. We had 2 to begin with, now we got 4 of them. What can we do with those 4 prime numbers that we have now? We can multiply them together and once again add 1. It's amazing what that number 1 can do. If we multiply that all out together, and I've done so on a calculator, we get an output of 463, and we have a list of what? 1, 2, 3, 4 prime numbers now. Okay, notice that our last output, which was 22, written as 2 times 11, became an input in step 4 here. So notice as we go along that outputs become inputs further down the sequence. So here we've got 463 as an output, and 463, it turns out, and I checked this, it's pretty easy, is a prime number. Well, our output becomes an input in step 5. And we can multiply now. Our list of prime numbers is growing. We have what? 2 times 3 times 7 times 11. And our new input, which was our old output, is 463. And just like before, we add 1. Okay, 1. Okay, we multiply all these together, and we add 1. And that gives us 213,907, which is our new output, which would become an input if we went on. But I don't know if we need to go on for you to understand that we've proven something. If we take any one of these primes and divide it into 213,907, it will be just like the 22. We will get a remainder of, dum-da-da-dum, 1 of 1. So we know that 213,907 must either be a prime number that's not in our list, or its factors, like the 2 and 11, will be different primes than these. Because remember, these can't go into this number exactly. If it has factors, it has to be different numbers than these. Just like for 22, 22's factors have to be different than 3 and 7 because they do not go into 22 exactly because of the 1. Ta-da. All right. So there's a couple really amazing things to think about here. We actually have proven, because our list is just going to keep on going longer and longer with more prime numbers generated, either by what number we get or its factors. And that loop will actually go on forever. We've proven for sure that the prime numbers go on forever, which is an amazing thing to realize, not as a guess, but in math, you try to prove things. It's proven. Furthermore, the logic here is a loop. Output becomes input. Output becomes input. That idea, the idea of a loop like that, is absolutely central to computer programming. Your phone, your computer, our modern world are very much built partly on logic loops in programming. So this journey here is about math, but it's also really a good introduction to computer science. Logic loops, they really get used a lot. And now finally, what's this bit about money? Well, it turns out that on the internet, when we do banking or when we buy anything anywhere, people multiply gigantic prime numbers together in what are called encryption, RSA encryption methods. And those gigantic numbers that come from multiplying huge prime numbers together, turns out that even supercomputers cannot break them down or factor them quickly, which is why those kinds of gigantic, ginormous numbers are used to protect the money you have in bank accounts, the money you're spending, your identity. When you spend money on the internet, believe it or not, we are protected by gigantic prime numbers. It's only a multi-trillion-dollar industry. No big deal. At any rate, I hope that that's helpful and that you've enjoyed this adventure. There's one more little bit at the end I think that's worth thinking about, and that is that it turns out, an interesting property of prime numbers, that for any prime number bigger than 3, let's see if I can get this lined up nicely here. Yeah. For any prime number bigger than 3, if you square it, like 5 times 5 is 25, that's squaring 5. And if you subtract 1, the result you get will be exactly divisible by 24. So 5 squared is 25, 25 minus 1 is 24, and 24 divided by 24 is 1. Exactly divisible. Next prime number is 7. 7 times 7, what's that? 49. 49 minus 1, 48. 48 divided by 24 is 2. 11 times 11, 121. 121 minus 1 is 120. 120 divided by 24 is 5. Turns out this can be proven. How come when you square a prime number greater than 3, this appears to be true, that if you subtract 1, you'll get a number that will be exactly divisible by 24. We have a mystery on our hands. At any rate, this has been huge E factors. I think we had some huge factors that we talked about here in terms of protecting green rectangles, otherwise known as money. Wishing you an absolutely wonderful day and reminding you and me that math is both humbling and awesome. Have a great one. Bye.